We are talking about the generalized estimation equations and when we can use this model to analyze our data. So if you have a data that looks like this, these are subjects ID that they have been measured in different timeline, 0, 1, 2, for example, the first month, second month, and third month, or 3 points in time. And we measure their blood pressure here. So subject ID 1 is one person, 2 is the second person. So you can see that here the data is arranged in the long format. It's in the long format, not in the wide format. So you can, if you have other types of data, you should change it back to this format. So some of these people, for example, patient number 1 didn't receive the treatment, but patient number 4 received the treatment. So we want to know if the treatment was effective or not. So this model is the technique used for analyzing correlated data, especially longitudinal or cluster data, where measurements are not independent. So, the GE accounts for the correlation. So GE is ideal when you have repeated measurement like the data that I showed you, like blood pressure over time for each patient, or other types of data that look like that needs to account for the within subject within cluster correlation. So the second blood pressure of the patient is correlated to the first one. We cannot say that these are like independent of each other. So extension of GLM extends generalized linear model like logistic or Poisson regression handle the correlated observation. Later we will get back to here. Population average estimate, it provides estimates of the average effects in the population, and this is robust to misspecification. So even if we specify the wrong correlation structure, like here is the exchangeable, we start with the exchangeable, and there are autoregressive and other types of correlations. Even if we make a mistake and we provide the wrong correlation, so it is still consistent. This model still consistent. So it's a very good model and very powerful. So this is the example that I want to run the GEE model on this one. So if you understand this, you can actually run it on your data. So here we can analyze the repeated health measurements over time, the cluster randomized trial. So this example is a randomized trial, and longitudinal surveys where participants are measured multiple times. So the context, you are analyzing a data set where 30 patients had their blood pressure measured 3 different time points, and some patients received new treatment and some of them receive standard K. So treatment 0 is standard K, and treatment 1 is the antihypertensive treatment, new pill that you want to do the randomized controlled trial on. So you want to understand the effect of the treatment over time on blood pressure, accounting for repeated measurement within the patients. So the question that I have is, what statistical method is appropriate for analyzing this effect of treatment over time if we want to account for the repeated measurements within the same patients? So we cannot use simple linear regression, but you should be ready to answer why we cannot use this, and run a GE model in Python using the stat models. We can do this assessment, and we should be able to interpret the coefficients of the model and what do they tell us, the coefficients of the model, and how to interpret all the results that we get from this model. So we start, if you have all this codes, if you don't have it, you can write the similar ones. AI generated model can easily make a suitable code for your own data, but now I use this one. You can change the data set, or if the variable names are different, you can change them, but these are already tailored for this data set. So I go back to see this is my Google Colab. I think you all know how to deal with this one. So you make a new notebook in your drive using the function, and now when you have a new notebook, so you just copy and paste it here. We didn't copy this properly, so maybe we do this. It's not pasting, not sure why. Let me double check if it is possible to paste this here. It's not working. Copy here and paste it here. Oh, because it should be a lot. Okay, so I paste it already here. So the first step is just import the required data set, and after that they will give me load the data set and give me a summary of statistics, and then show the model summary for me and do the GENMOD for me. And this is the equation for the model. So it is the time effect, the treatment effect, and time and treatment effect. So there are things later we are going to study the parameters of this formula. So here, if I run this one, it will be run after a while. So it should be asking me to upload the data first after the installation of the required packages. So these are the packages that this block needs. So after this, it should be able to ask me to upload my data. So if I upload my data here, for example, the dataset GEE teaching dataset that I know, so it automatically analyze the data for me based on the time, treatment, and the subject ID. So subject ID should be in the first column, time and treatment should be specific variables, and blood underlying pressure is my outcome measure. So the data set looks like this. So this is just a sample from the the first four rows of the data set, and these are the summary statistics that I have. So it just gives me mean, standard deviation, and count of the rows. So we have 90 subject ID rows. So these are every person has 3 measurements, so it has 90. So if somebody has the missing variable, missing measurement, so you'll have less than 90. So you can see that this is the GENMOD summary here, that you can see 90 observations. These are 30 clusters, and minimum cluster size, maximum cluster size. So you can see these differently if you have missing data. And the other things here are the other characteristic of this regression result. So we are working with this. So intercept, we have time, we have treatment, and we have treatment and time. So these are the coefficient of regression here, and these are the z statistics, and these are the p-values that we can see. These are the confidence interval, the skewness of the model, and other things we can also see that. So let's interpret these results as I have it in the file. So let's go on and check. So Output explanation, I will just give it to you. Installation message, the first row that we talked about it. The upload confirmation, dataset preview, we talked about this one, and summary statistics. And this is GEMOD output. This is the one that we have to interpret. So the intercept 122.75 is the estimate blood pressure at time 0. So if the other variable in the model is 0, so that factor is gone, and the remaining thing is the estimate of blood pressure in the time 0 in the control group, because these two are 0. So time 0, control group is 0. So these two factors are going to be cancelled, and what is left is the blood pressure. So blood pressure at time 0 in the control group is the intercept. So time, when the time 0.57 is the coefficient, I guess, right? 0.57 is the coefficient here, and it is not significant, as we can see it here. 0.5 is the p-value. So the blood pressure doesn't significantly change over time in the control group. So because the other factor should be set to 0, so in the control group we say that. So the blood pressure doesn't change. The blood pressure is our outcome variable, right? It doesn't change over time. So if time changes, the blood pressure doesn't change. If we forget about the factor of the group, so group is the other factor. So if we put it in the 0, so group factor is gone, so we can say that blood pressure doesn't significantly change over time. So the treatment minus 5.74, it shows that the treated group, because the treatment, when it is the treatment group, it is 1, so it is 5.74 units lower than the control at the baseline. So we are also taking away the factor of the time. So when it's the baseline, it means the baseline, the treatment group starts 5.74 units lower than the control group. So the other thing that we have to take care is the time and treatment, the interplay of time and the treatment. This is what we were interested in to see. So in the treatment group, we were talking about the treatment group, blood pressure decreases more over time compared to the control group. So compared to the control group, because control group is 0 and the treatment group is 1, so compared to the control group, in the treatment group, blood pressure decreases over time. How much decreases? And it decreases 4.47, and this is statistically significant because of the p-value. So blood pressure decrease more. How much more? 4.47 more. It decreases, because we say decreases, we don't say minus anymore. So decreases more over time compared to the control group. So clinical interpretation for the students is that treatment shows a meaningful and significant downward trend in blood pressure over time. So this was how to do the GEE and how to interpret the results. And we are going to talk a little bit more how to interpret and why we actually use this model. So if you study until here, so please stop the video and run it for yourself one time and try to explain the model, the interpretation of the output for yourself. And from here we are going to explain more about the GE model and why we did that and what does it solve. So problem with the repeated measures is that when we measure the same patient multiple times, for example 3 time points in this data, these data points are not independent of each other. For example, patient's blood pressure on day 1 is likely similar to day 2 because this is the same person. So data of the blood pressure in day 1 and day 2 are very much correlated. So we have to take into account this. Traditional model failing if we want to interpret the results. So using a regular linear regression, assume all data points are independent. That would be underestimating the standard error that inflates the statistical significance and give misleading results. GE solves this. The GEE model accounts for the intra-subject correlation using a working correlation structure. This one that we used here was exchangeable, which assume equal correlation between any two time points for the same patient, time 1 and time 2, time 2 and time 3 in this example. So these are equal. We don't think that this correlation goes down or goes up or just mixed. Sometimes go up, sometimes go down. So these are exactly the same. First and second, second and third, or any other measurement that we have. So this is the exchangeable correlation that we used. So GE focus on the estimates average population level effect, make it ideal for clinical question. Does this treatment reduce blood pressure on average? So if we can answer this question, the model that we have to use is GEE. So these results show that we already talked about this. So if you want to repeat this, so please stop the video here and read this table once again to make sure that you understand this. So in this study, we tracked patients' blood pressure at 3 different time points. Some patients receive a new treatment while others did not receive the new treatment. Using this pattern is usually for the RCTs, right? So we can use this model in any RCT. Using GE, we found that the treatment group had a greater and significantly statistically significant reduction in blood pressure because of the minus in the treatment factor. Over time, compared to the control group, this suggests that the treatment is effective at lowering the blood pressure progressively over time. So this is the answer that we were looking for. This suggests that the treatment is effective at lowering, because of the minus in the coefficient, in lowering the blood pressure progressively over time because of the time treatment factor here. So monitor patient trends over time, not just one time value. GE helps to identify the interventions show benefits across time, which is more clinically meaningful than a single difference. So the formula that we were talking about this is this is our outcome, and all these are the factors that are going to predict. B0 is the intercept, beta 1 is effect of time, beta 2 is the effect of treatment, and beta 3 is the interaction of time and treatment. So this one was what we interpreted before. So you can see that this is the general formula for the linear regression, you remember, right? So the same concept can be done for the logistic regression. So from the results, the beta 0 is this much, the time coefficient, the treatment coefficient, and the interaction coefficient are this much, and these are the interpretations. So if you still have some thought about like how to interpret, please stop it here and read this table once again and repeat it for yourself, so you will completely understand how to interpret this. And the most important thing that we are talking about is a time treatment. So it's the most important, shows if treatment improves blood pressure at time goes on. Improves means lower the blood pressure in this case, right? And we understand it from the minus from the coefficient. So G doesn't estimate random effects like random mixed models. So maybe in another video I will explain a little bit more about the mixed effects if we want to change the correlation assumption that we had here. So this one until here is the most useful, that we use the correlation structure exchangeable, that all repeated measures equally correlated. The first and the second and third, these correlations assume to be the same and not fading or not mixed. So if you are thinking about other correlation structure, you should doing other types of correlation structure. So this video explained how to do GEE for most of the clinical trials. So please write some comments for me to see what part I need to explain more in the next video. And thank you for watching.
You know me. Longitudinal vibes, we keep it tight. Correlated but consistent, stats done right. We got clusters, we got time. Measurements repeat, but that's just fine. GLM had limits, couldn't flex till G stepped in. No complex recs. Population average, yeah, we aim wide. No random effects, just a smooth ride. Exchangeable or AR1, misspecify and we still get it done. G, yeah, you model that dependence with robust variance and statistical elegance. From hospitals to patient tracks, you keep the correlation, no need to backtrack. Binary, Poisson, or multinomial. G adapts, it's phenomenal. Repeated measures, bring it here. Longitudinal structure, ain't no fear. We estimate across the crowd. No subject bias, just clear and loud. Empirical sandwich, hold the bias. G roll strong, never pious. Account for what you cannot see. Within subject, within cluster, harmony. G, yeah, you model that dependence with robust variance and statistical elegance. Population means with precision grace. Even if the structure's off, we're still in place. Steady through time, correlated, but still alive.